Hello, and welcome to Late Night Physics. If you're fascinated by the strange and mind-bending world of quantum mechanics, you're in the right place. Before we dive deep into the mysteries of the quantum realm, take a moment to like, subscribe, and hit that notification bell so you never miss an exciting new episode. And while you're at it, let us know where you're watching or listening from. Whether you're tuning in from the comfort of your couch, or maybe you're halfway around the world, it's always exciting to see just how far quantum physics reaches. Now, as we journey through the bizarre and intriguing world of the very small, think about this. In a universe where particles can be in multiple places at once, where do you fit into this quantum puzzle? Where are you in the universe, and how does what you know shape the way you experience the world around you? Stick around as we explore the deepest mysteries of reality itself, unraveling the fabric of space and time. This is going to be an adventure you won't want to miss. So let's get started. Quantum physics, often seen as one of the most mind-bending areas of science, holds the key to understanding nature at its most fundamental level. It's the branch of physics that governs the behavior of particles far smaller than atoms, on the scale of atoms themselves, and even smaller still. It's in this world that the rules of everyday life, the familiar physics we use to build bridges or send rockets to space, simply don't apply. And yet, this microscopic world is not some abstract theory. It affects everything around us, from the technology we use daily to the way the universe itself behaves. One of the most profound contributors to quantum theory is a man named David Bohm. His work, often overlooked, radically challenged conventional quantum thinking. Unlike many of his contemporaries, Bohm didn't view quantum mechanics merely as a set of rules for predicting outcomes. He believed there was something deeper, something that was hidden beneath the surface of these seemingly random events. He proposed a holistic interpretation of quantum theory, suggesting that the world was not just a collection of isolated particles, but a unified whole. Bohm called this deeper layer of reality the implicate order. The implicate order was a game-changer in how we think about the universe. In this view, everything is interconnected, like an intricate web of relationships. This order suggests that what appears to be random or chaotic at the surface is actually the unfolding of a deeper underlying order, one we don't yet fully understand. Imagine the surface of a calm pond. The ripples you see on the surface are the effects of forces underneath the water, but those forces are not immediately visible. In Bohm's theory, the implicate order is like the depth of that pond, hidden from view, but crucial to the patterns we observe on the surface. But not everyone agreed with Bohm's ideas. One of the most famous interpretations of quantum mechanics, developed by Niels Bohr and his colleagues, is known as the Copenhagen interpretation. This theory suggests that particles, like electrons or photons, don't have definite properties, such as position or momentum, until they are observed. Before observation, they exist in a state of probability, where their location, for example, can be described only in terms of likelihood. Bohr argued that the act of measuring these particles essentially forces them into a single state. This concept was revolutionary, but it also led to some odd ideas. For instance, in the famous Schrödinger's cat thought experiment, a cat in a box is both alive and dead at the same time, until someone opens the box and observes the situation. It was as if reality itself depended on being watched. That's a concept that feels deeply strange, doesn't it? Now, the Copenhagen interpretation and Bohm's implicate order are two very different views on quantum reality, but they share one crucial understanding. Quantum mechanics governs the tiniest elements of our world. And while these theories may seem abstract, the implications are anything but. Quantum mechanics is not just theoretical. It shapes our world in very real, practical ways. From the microchips inside our smartphones to the lasers used in eye surgery, quantum principles are everywhere. In fact, without quantum mechanics, much of modern technology wouldn't be possible. The precise control of electricity, the functioning of GPS satellites, and even the magnetic resonance imaging MRI machines used in hospitals all rely on quantum effects. But quantum mechanics doesn't just change how we understand technology. It also changes how we view the universe itself. Take, for instance, the structure of matter. In quantum mechanics, the forces that hold atoms together, like electromagnetism, are described not as simple forces acting on separate particles, but as exchanges of energy carried by force-carrying particles called bosons. It's these tiny particles, like photons for light and gluons for the strong nuclear force, that act like messengers, transmitting forces between the particles in an atom. So when we're talking about the forces of nature, we're talking about a dance of particles communicating across unimaginable distances, even within atoms themselves. But what if quantum mechanics could explain more than just the microscopic? What if it held the secret to understanding the large-scale structure of the universe too? Some theorists believe that quantum mechanics might even play a role in the very origins of the universe. Concepts like quantum fluctuations, tiny, random variations in energy, could have been the spark that set off the Big Bang, creating the universe we live in today. And while this remains a topic of intense debate, it's clear that quantum mechanics touches on more than just the atom. It shapes the cosmos as well. As we continue our journey into the quantum world, remember this. At the core of quantum mechanics is the idea that things are not always as they seem. The universe is not just a series of predictable, deterministic events. Instead, it's a world of probabilities, of interconnected forces, and of mysteries yet to be uncovered. Whether we're talking about the strange properties of particles or the way light behaves, quantum mechanics reveals a world far stranger and more wondrous than we might have ever imagined. And as we explore it further, we'll uncover more of the mysteries that make up the very fabric of reality itself. The journey into quantum physics begins with a revolutionary idea from a scientist named Max Planck. In the year 1899, Planck was faced with a problem known as the ultraviolet catastrophe, a situation in which the laws of classical physics predicted that an object would emit an infinite amount of energy when heated. This didn't match up with what was observed in reality, where heated objects glow with a finite amount of light. To solve this problem, Planck proposed a radical idea. Instead of treating energy as a continuous flow, he suggested that energy could only be emitted or absorbed in small discrete amounts, which he called quanta. This quantum hypothesis, as it came to be known, marked the birth of quantum theory. Planck's idea was a game-changer, and although he didn't fully realize its implications, it would become the foundation for a whole new understanding of the universe. For Planck, energy was quantized, meaning it existed in packets rather than as a smooth, continuous flow. His work would lay the groundwork for a century of discovery and ultimately a revolution in physics. Now let's move ahead a few years to the early 20th century, when a young French scientist named Louis de Broglie introduced another radical idea that would shake the foundations of physics. De Broglie proposed that not only light, but matter itself could behave as both a particle and a wave. Before de Broglie, scientists had believed that particles like electrons were, well, particles, small solid bits of matter that behaved in a predictable way. But de Broglie had a different perspective. Drawing inspiration from the wave-like nature of light, he suggested that particles like electrons might also exhibit wave-like properties. This idea, known as wave-particle duality, was revolutionary. It meant that the very nature of matter wasn't as simple as we once thought. Matter was no longer just solid and discrete, it could also ripple and oscillate like a wave. This dual nature would become a central concept of quantum mechanics. To test this, scientists would later observe that electrons, when passed through a crystal, would create an interference pattern, much like light does. It was as if electrons, tiny as they were, had a mind of their own, acting like waves under certain circumstances and as particles in others. De Broglie's hypothesis opened the door to a much deeper and more complex view of the universe. As the years went by, the exploration of quantum ideas expanded even further. In 1928, an English physicist named Paul Dirac took the next big step, combining quantum mechanics with Albert Einstein's theory of special relativity. Dirac had a particular knack for uniting seemingly incompatible ideas, and his work led to the creation of quantum field theory, QFT. Quantum field theory is a framework that describes the behavior of particles as interactions with fields rather than as isolated discrete objects. It was this approach that allowed for the prediction of antimatter, the idea that for every type of particle, there must be a corresponding antiparticle, a particle with the opposite charge and properties. This idea was later confirmed with the discovery of the positron, the antimatter counterpart of the electron. Dirac's work didn't stop there. He also developed a famous equation, known as the Dirac equation, which elegantly described how particles like electrons behave at high speeds, near the speed of light. The equation was a breakthrough, not only because it combined quantum mechanics with relativity, but because it also explained how electrons could exist in states that were previously unimaginable. Dirac's contributions were monumental in shaping the modern understanding of quantum physics. But as quantum theory developed, it began to reveal even more perplexing ideas, ones that challenge our classical intuitions and force us to rethink the very nature of reality. One of the most profound challenges came in the form of John Bell, a physicist from Northern Ireland who, in 1964, published a theorem that would alter how we think about the universe. Bell's theorem is perhaps one of the most important results in the history of quantum mechanics, as it introduced the concept of quantum non-locality. Quantum non-locality is the idea that particles can be instantaneously connected, no matter how far apart they are. This runs counter to the classical view, which assumes that information can only travel at a finite speed. Nothing can move faster than the speed of light. But in quantum mechanics, particles that are entangled can instantaneously influence each other, regardless of the distance separating them. Bell's theorem showed that if quantum mechanics is correct, then the universe is deeply interconnected in ways we can't fully understand or explain with classical physics. It's as if particles, once entangled, share a hidden connection that transcends space and time. Bell's work has profound implications for our understanding of causality and locality, and it has been confirmed by numerous experiments since. While quantum mechanics was already transforming the way we understood the world, it wasn't just shaking up traditional physics, it was inspiring new frontiers of exploration. One of the most exciting developments of the late 20th century came from a brilliant physicist named David Deutsch. In 1985, Deutsch proposed the concept of the quantum computer, which would be fundamentally different from classical computers. Unlike traditional computers, which use bits to store information as either a 0 or a 1, a quantum computer uses qubits, quantum bits. Qubits have the ability to exist in a superposition of states, meaning they can be both 0 and 1 at the same time. This allows quantum computers to process vast amounts of information in parallel, solving complex problems far more efficiently than classical computers. Deutsch's idea was groundbreaking because it suggested that quantum mechanics could be harnessed not just for understanding the universe, but for creating entirely new types of technology. While the first quantum computers are still in development, the potential applications are vast. Quantum computing could revolutionize everything from cryptography to drug discovery, artificial intelligence, and beyond. The implications for information processing are staggering. Quantum computers could potentially solve problems that are completely out of reach for even the most powerful supercomputers today. As we look back on these groundbreaking ideas, it's clear that quantum physics is not just a theory confined to textbooks. It's a living, evolving field of science that continues to shape the world we live in. From the early quantum hypothesis of Max Planck to the radical insights of David Deutsch, quantum theory has pushed the boundaries of human knowledge, forcing us to confront a reality that is far stranger and more complex than we ever imagined. It's a reality where matter and energy are no longer simple, where particles behave both like waves and like particles, and where the universe itself is interconnected in ways we're just beginning to understand. The work of these pioneers, Planck, de Broglie, Dirac, Bell, and Deutsch, has opened up a universe of possibilities, and as we continue to explore the quantum world, there's no telling where the next discovery will take us. One of the most fascinating aspects of quantum mechanics is the idea of wave-particle duality. This concept reveals that light and matter, which we once thought of as either waves or particles, actually behave as both, depending on the situation. It's a mind-bending realization that takes us far beyond classical physics, where we were used to thinking about particles as solid, discrete objects, and waves as continuous, undulating phenomena. The story of wave-particle duality begins with light. For centuries, light was a subject of great debate among scientists. Some, like Isaac Newton, believed light to be composed of tiny particles, which he called corpuscles. Others, including Christian Huygens, argued that light was a wave, spreading out in all directions like ripples on a pond. It wasn't until the early 20th century that the true nature of light began to emerge. In 1905, Albert Einstein published a paper that would change everything. He proposed that light was not just a wave, but also a stream of discrete particles, which he called quanta, later known as photons. Einstein's work on the photoelectric effect, for which he would later win the Nobel Prize, demonstrated that light could behave like particles in certain conditions. The photoelectric effect occurs when light shines on a material, causing electrons to be ejected from the surface. Classical physics had trouble explaining why light of a certain frequency could eject electrons, while light with a lower frequency, despite being more intense, couldn't. Einstein solved this puzzle by suggesting that light isn't a continuous wave, but instead comes in discrete packets of energy. These packets, or photons, carry energy that depends on their frequency. When a photon strikes an electron, it transfers energy to the electron, knocking it loose from the material. The energy of the photon is proportional to its frequency, and if the frequency isn't high enough, the photon doesn't have enough energy to release the electron. This was a groundbreaking idea. It showed that light, which had long been thought of as a continuous wave, also had particle-like properties. This discovery opened the door to quantum theory and set the stage for the exploration of wave-particle duality. Now, if light could act like both a wave and a particle, could matter behave the same way? Enter Louis de Broglie, a French physicist who, in 1924, proposed a radical idea. If light could be both a wave and a particle, then maybe matter too could have wave-like properties. De Broglie suggested that particles like electrons could exhibit wave-like behavior under the right conditions. This was a huge departure from classical physics, which treated particles and waves as entirely separate entities. De Broglie's theory was bold and groundbreaking, and it turned out to be correct. De Broglie's hypothesis suggested that all matter, not just light, has a wave nature. For example, an electron orbiting a nucleus could be thought of not just as a tiny particle, but as a wave with a specific wavelength. The wavelength of a particle, like an electron, is inversely proportional to its momentum. The more momentum it has, the shorter its wavelength. This concept of matter waves would later be confirmed by experiments that showed that electrons, when passed through a crystal, created an interference pattern, something you would typically see with waves of light. In fact, it was de Broglie's work that paved the way for the development of electron microscopes, which rely on the wave nature of electrons to achieve magnifications far beyond what is possible with light. But the wave-particle duality concept didn't stop with de Broglie. As quantum theory evolved, it led to even deeper, more profound ideas. One of the most influential contributions came from David Bohm, a physicist who, in the 1940s, developed a theory of quantum mechanics that included the idea of a quantum potential, a hidden, underlying force that guides the motion of particles. Bohm's theory was radical because it suggested that quantum particles are not just governed by a probabilistic wave function, as in the standard interpretation, but also by a deeper, non-local quantum field. This field is not directly observable, but it influences particles and their behavior in a way that goes beyond the wave-particle duality of traditional quantum theory. Bohm's idea of quantum potential suggested that particles were not just moving randomly in space, as the standard interpretation of quantum mechanics would suggest. Instead, they were being guided by this quantum potential, which, in Bohm's view, was a more fundamental aspect of reality than the particle itself. This theory implied that the universe was far more interconnected than we had previously realized, with hidden forces guiding the motion of particles at distance. Bohm's theory was at odds with the mainstream Copenhagen interpretation, which views quantum mechanics as fundamentally probabilistic. Bohm's work, while not widely accepted at the time, has since gained renewed attention and offers a fascinating alternative view of the quantum world. As we've seen, wave-particle duality isn't just a quirky feature of light, it's a fundamental aspect of the universe. It stretches across both light and matter, offering a new way to understand the strange behavior of the microscopic world. This duality is not just a theoretical idea. It has been confirmed through countless experiments that show particles behaving like waves under certain conditions, and waves behaving like particles in others. One of the clearest demonstrations of wave-particle duality comes in the form of quantum interference. In the famous double-slit experiment, when light or electrons are passed through two slits, they create an interference pattern on the other side, as if they were waves spreading out and overlapping. But when you observe the particles, they act like particles, going through one slit or the other. This experiment shows that particles like electrons can exhibit wave-like properties, and light can exhibit particle-like properties, depending on how we choose to measure them. It's a phenomenon that lies at the heart of quantum mechanics, challenging our very understanding of reality. Another example of wave-particle duality is electron diffraction. When a beam of electrons is directed at a crystal, it creates a diffraction pattern, just like light waves passing through a grating. This is direct evidence that electrons, despite being particles, behave like waves in certain circumstances, and just as light waves can create interference patterns, so too can electrons, showing that the boundary between waves and particles is not as clear-cut as we once thought. Wave-particle duality also plays a crucial role in quantum technologies. For instance, electron microscopes, which rely on the wave-like properties of electrons, allow us to see objects at a level of detail far beyond what is possible with traditional optical microscopes. The development of lasers, computers, and other modern technologies also owes much to our understanding of light's dual nature. Without the insights provided by wave-particle duality, many of the technologies that shape our world today would not be possible. So, while wave-particle duality might seem strange and counterintuitive, it's at the heart of the quantum world. It reminds us that reality is not always what it seems at first glance. Light and matter, far from being separate and distinct, are two sides of the same quantum coin, each capable of exhibiting both wave-like and particle-like behavior, depending on how we observe them. And as we continue to explore the quantum world, we'll find that this duality holds the key to unlocking some of the universe's deepest mysteries. One of the most puzzling and intriguing aspects of quantum mechanics is the phenomenon of quantum entanglement. It's a feature of quantum theory that challenges our very notions of space, time, and locality. The concept was first introduced by Albert Einstein, who famously referred to it as spooky action at a distance. To understand why Einstein had such a strong reaction, we need to take a step back and look at what quantum entanglement actually is, and why it seemed so strange to him. In the simplest terms, quantum entanglement occurs when two or more particles become linked, or entangled, in such a way that their states are interconnected. This means that no matter how far apart these particles are, changing the state of one particle will instantly affect the state of the other, even if they are light years apart. This instantaneous connection seems to defy the speed of light limit, set by Einstein's theory of relativity. And this is exactly why Einstein called it spooky. It seemed to suggest that information could travel faster than light, violating one of the fundamental principles of modern physics. But Einstein wasn't alone in questioning the validity of entanglement. For many years, the idea was seen as one of the more bizarre and unpalatable aspects of quantum mechanics. The standard interpretation of quantum mechanics, which had been developed by Niels Bohr and others in the early 20th century, relied on the notion that particles exist in a superposition of states until measured. In other words, a particle can be in multiple states at once, and only when we observe it does it collapse into one definite state. However, when particles become entangled, the situation becomes far more perplexing. If two entangled particles are separated by vast distances, how does the change in one particle's state immediately affect the other? It's as though the particles are communicating with each other faster than light, which seems impossible according to our current understanding of space and time. In the 1960s, a physicist named John Bell took a closer look at this issue. Bell was fascinated by the strange implications of quantum entanglement, and he wanted to test whether quantum mechanics was truly consistent with the idea of locality, the principle that information cannot travel faster than light. Bell formulated a set of inequalities, now known as Bell's inequalities, that could be experimentally tested to determine whether or not quantum mechanics was violating the principles of locality. These inequalities essentially set limits on the correlations between measurements made on entangled particles. If quantum mechanics were correct, these inequalities would be violated, proving that entanglement was real and that particles could influence one another instantaneously, even across vast distances. Bell's theorem, published in 1964, demonstrated that if quantum mechanics were correct, then the world of quantum particles was indeed non-local. This was a radical idea, one that suggested that the universe behaves in ways that are entirely different from our everyday experience. But while Bell's theorem showed that non-locality was a natural consequence of quantum theory, it wasn't enough on its own to convince many scientists. After all, theory alone isn't enough to change minds in physics. Experiments were needed to test Bell's predictions. Enter Alain Aspect, a French physicist whose pioneering experiments in the early 1980s provided the first definitive evidence for quantum entanglement. In 1982, Aspect and his team performed a series of experiments that tested Bell's inequalities, using entangled photons instead of electrons. The results were striking. They showed that the correlations between the measurements of the entangled photons violated Bell's inequalities, providing solid experimental evidence that quantum entanglement was real, and that the particles were indeed acting non-locally. This was a landmark moment in the history of physics, and it confirmed that quantum mechanics was not just a theoretical curiosity. It had real, observable consequences. The results of Aspect's experiment weren't just a confirmation of the strange nature of quantum mechanics. They also had profound implications for the future of technology. One of the most exciting developments that has come from the study of quantum entanglement is the field of quantum teleportation. Quantum teleportation allows for the transfer of quantum information between two particles, without the particles themselves ever having to physically travel between the locations. This might sound like science fiction, but it's a real phenomenon that has been demonstrated experimentally. Anton Zeilinger, an Austrian physicist, has made major contributions to the field of quantum teleportation. In 1998, Zeilinger's team successfully demonstrated quantum teleportation of quantum states using entangled particles. By entangling two particles, and then using a third particle to send a classical signal, they were able to teleport the quantum state of one particle to the other, no matter how far apart they were. This experiment was a monumental step in our understanding of how quantum information can be transmitted, and it opened the door to the possibility of quantum communication systems that are secure, fast, and fundamentally different from the classical communication systems we use today. But quantum entanglement isn't just about teleportation and communication, it also challenges our fundamental understanding of the nature of reality itself. This is where the work of Hans-Peter Dürr comes into play. Dürr, a German physicist, proposed an alternative interpretation of quantum mechanics, known as the transactional interpretation. According to this interpretation, quantum events are not simply probabilistic, as described by the standard Copenhagen interpretation, but are instead a result of transactions between particles. These transactions are a form of exchange between the past and the future, where particles are influenced not just by their past interactions, but also by future possibilities. In Dürr's view, quantum entanglement is not just about particles being instantaneously connected across space. It's about a deeper, non-local exchange of information that transcends our usual understanding of time and space. This interpretation offers a new way of thinking about quantum phenomena, including entanglement, by proposing that particles do not just interact with each other in the present, but are influenced by a broader, more interconnected reality. Dürr's work invites us to reconsider the very nature of reality, suggesting that the universe is far more interconnected and dynamic than we have previously understood. So, where does all this leave us? Quantum entanglement and non-locality have been experimentally confirmed, and they have opened up new possibilities for technology, such as quantum teleportation and quantum communication. But they also challenge our fundamental concepts of space, time, and causality. Einstein's objections to spooky action at a distance may have seemed valid based on our classical understanding of the world, but quantum mechanics has proven that the universe operates in ways that defy our expectations. Whether we're talking about quantum teleportation, quantum computers, or even a new understanding of the interconnectedness of all things, entanglement and non-locality are at the heart of a new quantum view of the universe. And as we continue to explore these ideas, there's no telling what strange and exciting discoveries await us on the horizon. Imagine for a moment that you could be in two places at once. You could take a walk in the park while also sitting at home reading a book, or even experience multiple paths in life simultaneously. This might sound like something out of science fiction, but in the realm of quantum mechanics, it's not as far-fetched as it seems. In fact, it's a central idea in one of the most radical interpretations of quantum physics, the many worlds interpretation, or MWI, proposed by physicist Hugh Everett in 1957. Everett's many worlds interpretation offered a bold solution to one of quantum mechanics' most puzzling paradoxes, the question of what happens when we measure a quantum system. According to the Copenhagen interpretation, which was developed by Niels Bohr and others in the early days of quantum mechanics, a quantum system exists in a superposition of multiple possible states until it is measured. At that point, the system collapses into one definite state. Either the particle is here, or it's there, but not both. However, Everett had a different idea. Rather than imagining that the act of observation forces the wave function to collapse into a single state, He proposed that all the possible outcomes of a quantum measurement actually happen, each in its own branch of reality. This means that instead of a single outcome emerging when a measurement is made, the universe splits into multiple parallel realities, each corresponding to one of the possible outcomes of the quantum event. In this view, every time a quantum measurement occurs, the universe branches into multiple versions of itself, where every possible outcome of the measurement exists in its own separate reality. This idea, though mind-boggling, offers a fascinating and elegant way of understanding quantum mechanics. In Everett's interpretation, the apparent randomness of quantum events is simply the result of an observer perceiving only one branch of the ever-expanding multiverse. In some sense, the universe doesn't choose a single path, it simply becomes every possible path. If you've ever wondered what happens when you face a tough decision, in Everett's world, there's a version of you who made each choice. You didn't just pick one path, you experienced all of them in parallel. Everett's many worlds. Interpretation provides a striking contrast to the Copenhagen interpretation, which involves the collapse of the wave function upon measurement. In Copenhagen, before an observation is made, particles like electrons exist in a superposition, where they can occupy multiple states at once, being in two places at the same time, for example. But once an observation is made, the wave function collapses, and the particle assumes a definite state. For Bohr and his followers, this collapse was fundamental to understanding quantum behavior. Without it, quantum mechanics would simply be incomplete. But Everett's solution was different. He didn't think the wave function collapsed at all. Instead, he believed that every possibility described by the wave function was realized in a different branch of the universe, existing in parallel. While Everett's idea was revolutionary, it didn't initially receive much attention. The notion of a multiverse, of splitting universes with every quantum event, was difficult for many scientists to swallow. However, his work laid the foundation for future developments in quantum theory. One key contributor to the growth of the many worlds interpretation was physicist Bryce DeWitt, who, in the 1960s, helped formalize the mathematical framework for MWI. DeWitt was instrumental in extending Everett's ideas into a broader, more coherent theory. He recognized that the many worlds interpretation had implications far beyond just the measurement problem. It could potentially be applied to understand the entire structure of the universe. DeWitt's work made MWI a more solid and formalized part of quantum theory, offering a fresh perspective on how the universe might behave at the most fundamental level. In addition to formalizing the many worlds interpretation, David Deutsch, a British physicist, recognized the importance of MWI in the field of quantum computation. Deutsch's contributions in the 1980s demonstrated that the principles of MWI were not just philosophically intriguing, but also practically significant in the development of quantum computers. In a traditional computer, information is stored in binary bits, each of which can either be a 1 or a 0. But in a quantum computer, information is stored in quantum bits, or qubits, which can exist in a superposition of both 1 and 0 at the same time. Deutsch showed that a quantum computer, in a sense, explores multiple solutions simultaneously, taking advantage of the many possible states a qubit can occupy. This idea draws directly from the many worlds interpretation, where the quantum computer doesn't collapse into one solution after a measurement. Instead, it effectively branches into different worlds, each representing a different computational path. MWI provides a natural explanation for the power of quantum computers, as it allows quantum systems to process vast amounts of information in parallel. Quantum computers, powered by the principles of MWI, could potentially solve problems that are currently intractable for classical computers, like simulating complex molecular structures or factoring large numbers for cryptography. As MWI began to gain more attention in quantum computing, it also caught the interest of Renato Renner, a physicist who specializes in quantum information theory. Renner's work explores how quantum mechanics can be applied to information theory, shedding light on the nature of quantum superposition and the role it plays in the development of secure communication systems and encryption technologies. One of the key challenges Renner tackles is understanding how quantum superposition can be used to preserve the privacy and security of information, which is vital for the future of cryptography. In quantum mechanics, superposition allows particles to exist in multiple states simultaneously, which has profound implications for information processing. In classical computing, a bit is either in one state or the other, while in quantum computing, a qubit can be in a superposition of both states, greatly increasing the power of computational systems. Renner's research has helped us understand how these superpositions work in the context of quantum information, particularly in terms of how quantum systems maintain their coherence across multiple possible states. But how do all of these ideas fit together? The many worlds interpretation provides a unique way of understanding quantum mechanics, especially when it comes to superposition and the role of observers. In MWI, superposition is not just a temporary state that collapses when observed. Instead, all possible outcomes of a quantum event exist in parallel. This gives us a radically different view of reality, one where the universe doesn't choose one path, but branches into every possible outcome, each occurring in a separate parallel world. It's as if each decision, each measurement, causes the universe to split, creating an infinite number of parallel realities, each following a different version of events. The implications of MWI go beyond just understanding quantum systems. They challenge our very conception of reality itself. If every possibility truly exists, then what does that say about the nature of time, space, and causality? Are we merely travelers in a vast branching multiverse, where every potential outcome of our actions is realized in some parallel world? As scientists continue to explore the many worlds interpretation, they're not just seeking to understand quantum phenomena, they're also grappling with the fundamental nature of existence. The answers they find could lead us to a deeper understanding of reality, one that might even change how we perceive our place in the universe. In the end, the many worlds interpretation offers a thrilling, mind-expanding view of the quantum world, one that pushes the boundaries of imagination and challenges our classical ideas of reality. It shows us that quantum mechanics, far from being a strange and isolated realm, could hold the key to understanding the deeper structure of the universe itself. And with the advancements in quantum technology, from quantum computing to quantum information theory, the ideas first proposed by Everett and expanded by others like DeWitt, Deutsch, and Renner are becoming more than just abstract concepts. They're paving the way for the future of technology and our understanding of the cosmos. In the world of computing, the idea of quantum computers has long been a tantalizing dream, one that promised to solve problems too complex for even the most advanced classical computers. But it wasn't until the brilliant physicist Richard Feynman began discussing the concept in the 1980s that the possibility of quantum computers started to feel more like a reality. Feynman's insight was both simple and profound. Traditional computers, which process information using bits that are either 1 or 0, could never efficiently simulate the behavior of quantum systems. After all, quantum systems themselves behave according to the laws of quantum mechanics, where particles exist in multiple states simultaneously. This makes simulating quantum systems with classical computers not just difficult but practically impossible. Feynman realized that to simulate quantum systems effectively, we needed a new kind of computer, one that could harness the very principles of quantum mechanics. And so, he proposed the idea of a quantum computer, a machine that could use quantum bits, or qubits, to process information. Unlike classical bits, which are either 1 or 0, qubits can exist in superpositions, where they can be both 1 and 0 at the same time. This property, combined with another quantum phenomenon called entanglement, allows quantum computers to process vast amounts of data simultaneously. This ability to explore multiple possibilities in parallel gives quantum computers the potential to solve certain problems exponentially faster than classical computers. But while Feynman's idea was groundbreaking, it was still very much in the realm of theory. The next significant leap came in the early 1990s, when David Deutsch, a British physicist, expanded on Feynman's ideas and formalized the concept of the quantum Turing machine. Deutsch proposed that quantum mechanics could be used to create a computer that would be far more powerful than any classical machine. He built on the work of Alan Turing, whose Turing machine had provided a theoretical model for all classical computers. Deutsch's quantum Turing machine was based on the same principles, but with one major difference. Instead of using classical bits, it used qubits. This meant that a quantum computer, in theory, could perform parallel computations, carrying out many different calculations at the same time. Deutsch's quantum Turing machine showed that quantum computers weren't just a theoretical curiosity, they were mathematically possible. This opened the door for further development in the field of quantum computation, and in the years that followed, researchers began to develop algorithms that could harness the power of quantum computing. One of the most famous of these algorithms is Grover's algorithm, developed by Lovegrover in 1996. Grover's algorithm is designed to speed up database searches. In a classical search, you would have to check each entry one by one, taking time proportional to the size of the database. But Grover's algorithm allows quantum computers to search an unsorted database in square root time, which means that a database with 1 million entries would only take about 1,000 steps to search, instead of 1 million. While this might not sound like a huge difference at first, it's a game changer when you think about how this speedup could be applied to real-world problems, like searching through vast amounts of data or analyzing complex systems. Another landmark development in quantum computing came with Shor's algorithm, developed by Peter Shor in 1994. Shor's algorithm demonstrated that quantum computers could do something that was previously thought to be impossible: factor large numbers exponentially faster than classical computers. Factoring large numbers is the backbone of many encryption systems, including the widely used RSA encryption. RSA relies on the fact that factoring large prime numbers is incredibly difficult for classical computers, but with Shor's algorithm, a quantum computer can factor large numbers in a fraction of the time, making many of our current encryption systems obsolete. The implications of Shor's algorithm are profound, not just for encryption, but for the entire field of cybersecurity. Quantum computers, once fully developed, could potentially crack many of the cryptographic systems that we rely on today, which means that new quantum-resistant encryption methods will need to be developed. But the exciting thing about Shor's algorithm is that it shows quantum computers are not just faster, they are fundamentally different from classical computers. They offer the potential for entirely new ways of thinking about information processing, and that's what makes them so exciting. As the field of quantum computing has progressed, many companies have invested heavily in its development. IBM, Google, and Microsoft are all working on building the first practical quantum computers, but it's Google that made a particularly significant leap in 2019 when it claimed to have achieved quantum supremacy, the milestone where a quantum computer performs a task that is practically impossible for classical computers to accomplish. Google's Sycamore processor, a 53-qubit quantum computer, successfully completed a complex computation in just a few minutes, a task that would have taken a classical supercomputer thousands of years to complete. This achievement marked a major turning point in the field of quantum computing, signaling that quantum computers are no longer just theoretical, they are now becoming a reality. One of the key figures in the development of quantum supremacy is John Preskill, a physicist at the California Institute of Technology. Preskill coined the term quantum supremacy to describe the point at which quantum computers can outperform classical computers at a specific task. His work has been instrumental in shaping the conversation around quantum computing and its potential applications. The achievement of quantum supremacy by Google is an exciting milestone, but it's important to remember that we're still in the early stages of quantum computing. There is still a long way to go before quantum computers can be used to solve real-world problems on a large scale. The current quantum computers, while impressive, are still fragile and prone to errors, and they require very specific conditions to function, such as extremely low temperatures. Despite these challenges, the progress in quantum computing is undeniable. Companies like IBM are already working on making quantum computers more accessible, with their IBM Q platform offering cloud-based access to quantum processors for researchers and developers. Meanwhile, Microsoft is exploring a different approach, using topological qubits, which may be more stable than the traditional qubits used by other companies. There are also smaller startups like Rigetti Computing and IonQ that are pushing the boundaries of quantum computing in new and exciting ways. These developments signal that quantum computing is rapidly moving from the realm of theoretical research into the practical world, where it could have transformative effects on industries ranging from pharmaceuticals to artificial intelligence. While quantum computers still have a long way to go before they can tackle the big real-world problems, the potential is enormous. Quantum computing is not just about faster calculations, it's about new ways of thinking about computation itself. The principles of quantum mechanics, with their strange properties like superposition and entanglement, open up entirely new avenues for information processing. In the future, quantum computers could revolutionize fields like materials science, drug discovery, and climate modeling by allowing us to simulate complex systems that were previously out of reach. As we look to the future of quantum computing, we can expect to see more breakthroughs, more experiments, and more progress. The dream that Feynman and others first envisioned is starting to become a reality, and we are just beginning to unlock the incredible potential of quantum information processing. Whether it's cracking codes with Shor's algorithm, speeding up database searches with Grover's algorithm, or simulating the universe with quantum computers, the possibilities are limitless. It's an exciting time to be a part of the quantum revolution, and the journey has only just begun. Quantum field theory, or QFT, is one of the most powerful frameworks we have for understanding the fundamental forces of nature. It builds on the idea that what we think of as particles, like electrons or photons, are actually excitations or vibrations in an underlying field. Imagine a field as a kind of invisible ocean that stretches throughout all of space, and the particles we observe are simply disturbances in this ocean, much like waves rippling across the surface of water. In classical physics, we tend to think of particles as distinct solid objects, little marbles bouncing around in space, but QFT flips that idea on its head. In the quantum world, particles are not solid objects. They're more like ripples in a field, each corresponding to a specific type of particle. The electron, for example, is an excitation of the electron field, and the photon is an excitation of the electromagnetic field. Each of these fields permeates all of space, and what we see as a particle is just a localized disturbance in one of these fields. This concept of particles as excitations in quantum fields was developed in the early 20th century and became one of the most successful ideas in modern physics. It allows us to explain a wide range of phenomena, from how atoms hold together to the forces that govern the behavior of the universe. But what's fascinating about QFT is that it doesn't just describe the behavior of particles, it also explains the interactions between them. For example, when two electrons interact through the electromagnetic force, they do so by exchanging photons, particles of light. In the language of QFT, these photons are the force carriers of the electromagnetic field, mediating the interaction between the electrons. This concept is a cornerstone of quantum electrodynamics, QED, which is one of the most successful quantum theories to date, describing how light and matter interact at the quantum level. But if particles are just excitations in fields, that raises some interesting questions. What are these fields made of? How do they interact with each other? And how do they relate to the fabric of reality itself? Enter Gerard 't Hooft, a Nobel laureate who proposed a discrete structure for quantum fields in the 1970s. Most of QFT relies on the idea that fields are continuous, meaning they exist smoothly throughout space. However, 't Hooft suggested that quantum fields might actually be made of tiny, indivisible units, like cells in a cellular automaton. A cellular automaton is a grid of cells, each of which can be in one of a finite number of states, and the system evolves based on simple rules. In the same way, 't Hooft speculated that quantum fields might be composed of discrete, fundamental units that give rise to the continuous behavior we observe in the world. This idea is still speculative, but it points toward the possibility that spacetime itself may not be infinitely smooth at the smaller scales. Instead, it might be made up of discrete building blocks, each interacting in complex ways to produce the continuous fabric of reality that we experience. This idea ties in with another fascinating concept in quantum mechanics known as the Casimir effect. The Casimir effect is a phenomenon that arises due to quantum fluctuations in the vacuum of space. Even in the vacuum, which we think of as empty, quantum fields are constantly fluctuating. Particles and antiparticles are constantly being created and annihilated in pairs. These fluctuations give rise to tiny forces that are invisible in our everyday experience, but can be measured in the lab. The Casimir effect specifically occurs when two metal plates are placed very close together in a vacuum. The quantum fluctuations between the plates are different from those outside the plates, leading to a measurable force that pushes the plates together. This is one of the first experimental confirmations of the reality of quantum fields, showing that even in empty space, these fields are actively fluctuating. The Casimir effect serves as a reminder that the vacuum of space is far from empty. It's a dynamic, ever-changing sea of quantum fields, and this insight has profound implications for how we understand the fabric of reality itself. If the vacuum is a seething mass of quantum fluctuations, what does that mean for the spacetime that we live in? Is space itself somehow built from these fluctuations, and could the structure of spacetime itself be quantized? This idea of a quantized space-time brings us to the work of Carlo Rovelli, an Italian physicist who has contributed significantly to the theory of loop quantum gravity. Rovelli's work explores the possibility that space-time is not a smooth continuum, but rather made up of discrete units, or quantum loops, at the smallest scales. In his theory, space-time is a kind of network made up of interconnected loops that form the structure of the universe at the quantum level. These loops are the building blocks of space-time itself, and they give rise to the familiar fabric of space and time that we observe in the macroscopic world. Rovelli's theory offers an alternative to string theory, another approach to quantum gravity. While string theory posits that the fundamental building blocks of reality are tiny vibrating strings, loop quantum gravity suggests that space-time itself is made of tiny loops, and these loops give rise to the familiar geometry of space-time that we experience. According to Rovelli's theory, at the smallest scales, on the order of the Planck length, which is about 1/10,000 trillionth of a meter, space-time is quantized. It's not continuous, but is instead made up of these discrete loop-like structures. This has far-reaching implications, especially when it comes to understanding the true nature of gravity, the force that governs the large-scale structure of the universe. But let's zoom out for a moment. While we've been talking about quantum fields and their role in the fabric of space-time, it's important to remember that quantum fields are not just theoretical. They're essential to understanding the fundamental forces of nature. From electromagnetism to gravity, the forces that shape our universe are mediated by quantum fields. Each of these forces has its own associated field, which permeates all of space. Electromagnetism, for example, is mediated by the electromagnetic field, and the force of gravity, according to quantum field theory, is mediated by the gravitational field. Though, as of now, we don't yet have a complete quantum theory of gravity. The strong nuclear force and the weak nuclear force, which govern the behavior of particles inside atoms, are similarly mediated by quantum fields, known as gauge fields. These fields are responsible for holding atomic nuclei together and for processes like radioactive decay. What's amazing about QFT is that it provides a unified framework for understanding how all of these forces interact at the quantum level, showing that the universe is connected by an invisible network of fields. But quantum fields aren't just about forces. They also define the very nature of matter itself. The Higgs field, for instance, is responsible for giving particles mass. Without the Higgs field, particles would zip around the universe at the speed of light, with no mass to slow them down. The discovery of the Higgs boson at the Large Hadron Collider in 2012 confirmed the existence of this field, which had been theorized decades earlier. The Higgs field is a perfect example of how quantum fields are not just abstract concepts, but real, measurable phenomena that shape the universe in profound ways. As we continue to explore the mysteries of quantum fields, we're uncovering new and exciting insights into the nature of reality itself. Whether we're looking at the Casimir effect, loop quantum gravity, or the fundamental forces of nature, we're seeing that the universe is far more intricate and interconnected than we could have ever imagined. The quantum fields that permeate all of space are not just the background against which the universe plays out. They are the very fabric of reality itself, shaping everything from the tiniest particles to the largest cosmic structures. And as we continue to probe deeper into the quantum realm, we're bound to discover even more mysteries that will challenge our understanding and reshape our view of the universe. For over a century, physics has been guided by two monumental theories: Einstein's theory of general relativity and quantum mechanics. General relativity, published by Albert Einstein in 1915, describes the force of gravity and how massive objects curve the fabric of space-time. According to general relativity, objects like stars, planets, and black holes influence the curvature of space-time, which in turn affects how objects move. This theory has been incredibly successful at explaining the behavior of large-scale systems, from the motion of planets to the dynamics of galaxies. Its predictions have been confirmed by countless experiments and observations, from the bending of light around massive objects to the existence of black holes. On the other hand, quantum mechanics governs the behavior of the smallest particles in the universe. Like atoms and subatomic particles, it's a world where particles can exist in multiple states at once, where their positions and velocities are uncertain until measured, and where forces are mediated by discrete particles like photons and gluons. Quantum mechanics has revolutionized our understanding of the microscopic world, and its predictions have been confirmed in thousands of experiments. The development of technologies like semiconductors, lasers, and quantum computers relies on the principles of quantum mechanics. However, these two theories, general relativity and quantum mechanics, are fundamentally incompatible. General relativity deals with the smooth, continuous curvature of space-time, whereas quantum mechanics describes the universe in terms of discrete probabilistic events. One of the greatest challenges in modern physics is reconciling these two frameworks, as they provide fundamentally different views of reality. For instance, general relativity describes gravity as the warping of space-time, while quantum mechanics treats forces as being mediated by particles. When we try to apply both theories at once, especially in extreme environments like black holes or the very beginning of the universe, they break down, and we end up with mathematical inconsistencies. This is where the search for quantum gravity comes in, a theory that could unite general relativity and quantum mechanics into a single, cohesive framework. One of the key figures in the search for quantum gravity is Lee Smolin, a theoretical physicist whose work has focused on loop quantum gravity, LQG. Loop quantum gravity is an approach that attempts to quantize spacetime itself. In Smolin's view, spacetime is not a smooth continuum as described by general relativity, but is instead composed of tiny, discrete units, much like the pixels on a digital screen. These units, which are loops or networks, form the very fabric of spacetime. According to LQG, the smooth geometry of spacetime emerges from the interactions of these fundamental building blocks at the quantum level. One of the exciting aspects of LQG is that it suggests that spacetime might have a granular structure at the smallest scales at the Planck length, which is around 10 to the minus 35 meters. This is incredibly tiny, far smaller than anything we can currently measure, but it has profound implications for how we understand the structure of the universe. According to LQG, the universe doesn't have a smooth, continuous geometry at the quantum level. Rather, space-time is made up of discrete loops that interact in complex ways. This idea challenges our traditional understanding of gravity and space-time and offers a new way to think about the fundamental nature of reality. Another important contributor to our understanding of quantum gravity is Roger Penrose, a British physicist and mathematician whose work on the nature of space-time has had a profound impact on both quantum mechanics and general relativity. Penrose has proposed an intriguing theory that connects quantum mechanics with consciousness. His theory suggests that consciousness arises from quantum processes occurring within the brain's neurons, but his work also has important implications for our understanding of spacetime itself. Penrose has proposed that the geometry of spacetime, especially near black holes and other extreme environments, may be influenced by quantum mechanical processes. This idea, often referred to as orchestrated objective reduction, OR, posits that spacetime may not just be a passive background for physical events, but may itself be influenced by quantum processes. Penrose's work challenges traditional ideas about spacetime by suggesting that the fabric of reality itself could be dynamic and influenced by quantum processes. This is in contrast to the classical view of spacetime as a static, unchanging backdrop for the events of the universe. Penrose's ideas connect the study of quantum mechanics with the nature of consciousness and the very fabric of reality, offering a novel perspective on the relationship between mind and matter. His work is also deeply intertwined with the search for quantum gravity, as he seeks to understand how quantum processes might influence the geometry of spacetime at the smallest scales. Meanwhile, another approach to unifying quantum mechanics and general relativity has been developed by Edward Witten, a theoretical physicist best known for his contributions to string theory. String theory is an ambitious framework that attempts to describe all the fundamental forces of nature, including gravity, as manifestations of one unified entity, vibrating strings. In string theory, the fundamental particles we observe, such as electrons and photons, are not point-like objects, but rather tiny, one-dimensional objects that vibrate in different ways. These vibrations give rise to the various properties of particles, like mass and charge. One of the most compelling aspects of string theory is its potential to unify all four fundamental forces of nature: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. This idea of a theory of everything has long been the holy grail of physics. an equation or framework that could explain the workings of the universe in one neat package. String theory offers a tantalizing possibility. It suggests that all the forces of nature could arise from the vibrations of fundamental strings, with each type of string vibration corresponding to a different force or particle. However, string theory faces significant challenges. One of the biggest obstacles is that the theory requires the existence of additional spatial dimensions, more than the 3 dimensions of space and 1 dimension of time that we experience in our everyday lives. In string theory, there could be as many as 10 dimensions. With the extra dimensions being curled up at extremely small scales, these additional dimensions are not something we can observe directly, but they are essential for the mathematical consistency of the theory. Despite the challenges, string theory remains one of the most promising approaches to quantum gravity, and it has led to many important insights in theoretical physics. As physicists continue to explore quantum gravity, the ultimate goal is to reconcile the 2 great pillars of modern physics: quantum mechanics and general relativity. Both of these theories have been incredibly successful in their respective domains. General relativity has explained everything from the orbit of planets to the behavior of black holes, while quantum mechanics has revolutionized our understanding of the microscopic world. But they are fundamentally incompatible, and the search for a theory that can unite them, what is often called the theory of everything, remains one of the biggest challenges in modern physics. In recent years, there have been some exciting developments. Loop quantum gravity offers a promising way forward, suggesting that space-time itself may be quantized at the smallest scales. String theory provides a different perspective, offering a unified framework for all the forces of nature, but it requires the existence of extra dimensions that are difficult to test experimentally. And physicists like Roger Penrose are exploring new ideas that connect quantum mechanics with the nature of consciousness and the fabric of reality itself. The search for quantum gravity and a theory of everything is still ongoing, and we may be on the cusp of some profound discoveries. But one thing is clear: the answers we're seeking have the potential to reshape our understanding of the universe in ways we can't yet fully imagine, whether we find them in the loops of quantum gravity or the strings of string theory. The path to unifying quantum mechanics and general relativity promises to unlock some of the deepest secrets of the cosmos. Time is one of the most fundamental aspects of our experience, yet when we dive into the world of quantum mechanics, it quickly becomes clear that time is much more mysterious than it might first appear. We all experience time flowing in one direction, what we call the arrow of time. This means that events in our lives, from the ticking of a clock to the aging process, seem to move forward, never backward. This one-way flow is a feature of everyday life that we take for granted. However, when we zoom into the quantum realm, time's role becomes far less clear. In fact, time's behavior at the quantum level doesn't always match up with our intuitive understanding of it. One of the main reasons time's flow feels natural to us is because it aligns with the second law of thermodynamics, which states that entropy, the measure of disorder in a system, always increases over time. In other words, systems naturally progress from states of lower entropy to higher entropy. This gives us the feeling that time is always moving forward, from the past to the future. But this law only explains the arrow of time at macroscopic scales. When we look at things at the quantum level, things get much more complicated. Quantum mechanics, the theory that governs the behavior of particles at the smallest scales, doesn't seem to have an inherent direction of time. The equations that describe quantum systems, like the Schrödinger equation, are actually time-symmetric. This means they work equally well whether time is moving forward or backward. In other words, quantum systems don't naturally prefer a forward direction in time. If you were to run a quantum system backward in time, the mathematics would still hold true, and the system would simply follow a reverse path. This stands in stark contrast to the macroscopic world, where we see time flowing one way. So, if quantum mechanics doesn't offer a built-in arrow of time, where does the one-way flow of time come from in our everyday experience? Julian Barber, a British physicist, has proposed a fascinating idea to tackle this problem. Barber suggests that time, as we understand it, may not be a fundamental part of reality at all. In his view, what we experience as time could be a byproduct of the way the universe evolves. Barber's idea is rooted in the concept of timelessness. According to him, time is an emergent property that arises from the relationships between objects in the universe. Rather than time being a fundamental ingredient of reality, it might simply be a way we experience the changes and interactions between particles galaxies, and other phenomena. Barber's perspective challenges our conventional understanding. If time isn't fundamental, how do we explain the way we perceive the world? Barber suggests that we should think of the universe as a collection of instantaneous configurations of all its particles, with each configuration representing a snapshot of reality. As the universe evolves, these snapshots change, and we experience this evolution as the passage of time. From this perspective, what we call the flow of time might simply be the change between one snapshot of the universe and the next. This idea allows for a deeper, timeless structure to reality, one where time emerges from the relationships between objects rather than being a fundamental property of the universe itself. But not all quantum thinkers agree with Barber's idea of timelessness. For example, David Bohm, a theoretical physicist, had a different view on the role of time in quantum mechanics. Bohm, who was critical of the mainstream interpretation of quantum mechanics, suggested that quantum theory might be governed by a deeper level of reality, one that operates symmetrically in time. In Bohm's view, the laws of physics would work the same way regardless of whether time moves forward or backward. He introduced the concept of the quantum potential, a guiding force that directs the motion of particles in ways that cannot be explained by classical physics alone. Bohm's theory has important implications for how we think about time. He proposed that the universe operates based on an underlying order, which he called the implicate order, that is hidden from our everyday experience. In this view, the apparent passage of time we experience is just one aspect of a deeper, more fundamental reality. The symmetry of time, which Bohm emphasized, suggests that the apparent arrow of time we observe in our daily lives might be an illusion. In a universe governed by the implicate order, time might not have a definite direction. Instead, the way we experience time, starting from the past and moving to the future, could be a result of how the underlying quantum world interacts with our macroscopic reality. Bohm's perspective opens up the possibility that the flow of time we feel so strongly is just one aspect of a much deeper, more intricate process. Another key figure in our exploration of time and its connection to quantum mechanics is Roger Penrose, whose work bridges the worlds of quantum physics, general relativity, and consciousness. Penrose has made several important contributions to our understanding of the nature of time, particularly in the context of consciousness. In his orchestrated objective reduction, OR theory, developed in collaboration with Stuart Hameroff, Penrose suggests that consciousness arises from quantum processes occurring within the microtubules of the brain's neurons. These quantum processes are thought to be influenced by the geometry of space-time, which, in Penrose's view, connects time and consciousness. Penrose's work has far-reaching implications for our understanding of time. In his theory, consciousness is deeply tied to quantum events that take place at the very smallest scales of the brain. These quantum events may involve objective reduction, a process in which quantum superpositions collapse spontaneously, based on the geometry of space-time. This process, according to Penrose, is not just a random event but is linked to the flow of time itself. In his view, the passage of time is not just a backdrop against which events happen. It is woven into the fabric of consciousness and reality at a quantum level. Penrose also posits that the flow of time might be fundamentally connected to the second law of thermodynamics, which states that entropy in a closed system always increases over time. For Penrose, the arrow of time is tied to the growth of entropy, and this growth is what gives us our sense of time moving forward. The mysterious connection between consciousness and the flow of time suggests that our perception of time might be as much about how we experience events as about the underlying laws of physics. So, what does quantum mechanics tell us about the flow of time, and can it provide any insights into the true nature of time itself? The more we learn about the quantum world, the more we realize that time might not be as straightforward as it seems. Quantum mechanics shows us that time is not a fixed, universal feature of the universe. Instead, it might be a property that emerges from the relationships between quantum systems. The theories of thinkers like Barber, Bohm, and Penrose suggest that time could be much more flexible and mysterious than we have ever imagined. As we continue to explore these ideas, we might find that time is not just the ticking of a clock or the aging of our bodies. It could be a dynamic, evolving feature of the universe, something that emerges from the interactions of quantum fields, consciousness, and the very structure of space-time itself. This could lead to a new, deeper understanding of time, not as a simple, linear flow, but as something far more intricate, tied to the fundamental nature of reality. As quantum mechanics continues to evolve, it may just hold the key to unlocking the true essence of time and its role in the fabric of the cosmos. One of the most profound mysteries that science continues to grapple with is the nature of consciousness, our ability to experience the world, to think, to feel, and to be aware of ourselves and our surroundings. It's a question that has intrigued philosophers and scientists alike for centuries, yet it remains elusive. What is consciousness, and how does it arise from the physical processes of the brain? Can it be explained purely by the interactions of neurons and chemical signals, or is there something deeper at play? Roger Penrose, a British physicist and mathematician, is one of the most well-known figures to have delved into this mystery. Penrose's theory, which has garnered significant attention over the years, suggests that consciousness may not be explainable by classical physics alone. In his book, The Emperor's New Mind, published in 1989, Penrose proposed that quantum processes in the brain could hold the key to understanding consciousness. Unlike classical processes, which operate in a deterministic manner, where the outcome of any event is fully determined by the initial conditions, quantum processes are fundamentally probabilistic. This means that at the quantum level, there is an element of randomness and uncertainty, where particles can exist in multiple states at once until observed, and events can unfold in multiple possible ways. Penrose argued that this quantum nature of reality might be involved in the processes of the brain that give rise to consciousness. He suggested that consciousness could not simply be the result of classical computations performed by neurons, as traditional theories of brain function suggest. Instead, Penrose proposed that the non-computational nature of quantum mechanics could explain the rich, subjective experience of consciousness. In his view, consciousness arises from a special kind of quantum process, one that involves the collapse of the wave function, a process that happens when a quantum system transitions from a superposition of multiple states to a single state upon measurement. Penrose's ideas about quantum processes and consciousness set the stage for another bold theory, developed by Stuart Hameroff, a professor of anesthesiology and psychology at the University of Arizona. Hameroff built on Penrose's ideas, developing what is known as the OR theory, which stands for Orchestrated Objective Reduction. Hameroff proposed that the key to understanding consciousness lies in microtubules, tiny tube-like structures found within neurons. These microtubules, which help to maintain the shape and structure of the cell, may also play a crucial role in quantum processing. According to OR, the microtubules act like quantum computers within the brain. They could theoretically harbour quantum states and enable quantum computations to occur in parallel. These quantum states are thought to influence neural processing, and in turn give rise to the subjective experience of consciousness. The orchestrated objective reduction in OR refers to the idea that quantum computations in the microtubules are orchestrated by the brain's neural activity, leading to an objective reduction of the quantum state, which we experience as conscious awareness. Essentially, the microtubules may allow the brain to process information in ways that are fundamentally quantum, rather than classical. While OR is still a speculative theory, it opens up intriguing possibilities for how quantum mechanics might be tied to our experience of consciousness. The theory has sparked debate and investigation, with some researchers exploring whether quantum coherence could be sustained in the warm, noisy environment of the brain, something that was once thought impossible. Others, however, remain skeptical, arguing that the brain is too warm and wet for quantum effects to persist for long enough to influence cognition. Nevertheless, Hameroff's work has drawn attention to the possibility that consciousness might not be fully explainable by classical physics alone, and that quantum mechanics could play a role in how we experience the world. As we move from the individual brain to the universe at large, the relationship between consciousness and quantum mechanics begins to take on even more profound implications. John Wheeler, a celebrated American physicist, had his own ideas about the role of consciousness in quantum mechanics. Wheeler's most famous contribution to quantum theory is his idea of participatory consciousness, which suggests that the very act of observation shapes the universe. In Wheeler's view, the universe does not exist in a definite state until it is observed by a conscious being. Rather than the world unfolding independently of us, Wheeler's theory suggests that we are actively involved in creating reality by observing it. Wheeler proposed that quantum mechanics cannot be fully understood without considering the role of the observer. The act of observation is not just a passive act of recording what is already there. It is an active process that determines the state of the quantum system. In other words, the universe does not exist in a definite state until it is measured, and this measurement is only meaningful when there is a conscious observer. Wheeler's idea is deeply philosophical, and it raises fascinating questions about the relationship between consciousness and reality. Are we, as conscious observers, fundamental to the very existence of the universe itself? While Wheeler's ideas about consciousness and observation are intriguing, they are far from universally accepted. Hans-Peter Dürr, a German physicist and student of David Bohm, offered a different view. Dürr's interpretation of quantum physics, known as the transactional interpretation, presents a novel approach to understanding the role of consciousness in quantum mechanics. According to Dürr, quantum mechanics is not just about probabilities and wave functions. It is about the interaction of the observer with the quantum system. The transactional interpretation suggests that particles don't just exist as probabilities in a wave function. Rather, they interact with the future and the past in a way that involves both offer and confirmation waves. These interactions are thought to be influenced by the observer, but they occur in a way that transcends the traditional understanding of measurement and observation. Dürr's interpretation suggests that consciousness is not simply an active participant in the collapse of the wave function, as Wheeler proposed, but rather that it plays a deeper role in shaping the interactions between the quantum world and the macroscopic world we experience. In Dürr's view, the observer is not just a passive witness to the unfolding of quantum events. Rather, the observer is deeply interconnected with the system, influencing the flow of events in a way that goes beyond the classical notion of observation. This interpretation of quantum mechanics aligns with David Bohm's ideas of an implicate order, where the universe is seen as a deeply interconnected whole, with the observer playing an essential role in the unfolding of reality. As we explore these different ideas, it becomes clear that quantum mechanics may offer important insights into the nature of consciousness and its relationship to the universe. The theories of Penrose, Hameroff, Wheeler and Dürr challenge conventional views of consciousness, suggesting that it may not be an entirely classical phenomenon at all. Instead, it could arise from quantum processes at the deepest levels of the brain, or even from the fundamental structure of reality itself. These theories provide a glimpse into a reality where the mind and the quantum world are not separate, but instead deeply intertwined. The role of consciousness in quantum mechanics also raises profound questions about the nature of reality. If consciousness can shape the outcome of quantum events, what does that say about the universe we live in? Are we active participants in the creation of reality, or is our perception of the world simply a byproduct of deeper quantum processes? These are questions that remain unresolved, but the exploration of consciousness through the lens of quantum physics offers an exciting path forward in understanding not just how we think, but how the universe itself works. In the end, the intersection of quantum mechanics and consciousness offers a fascinating window into the nature of mind, reality, and existence. Whether we are talking about quantum consciousness, participatory observation, or the transactional nature of quantum systems, it's clear that our understanding of the universe is far from complete. But as we continue to explore these ideas, we may just uncover some of the deepest mysteries of the mind and the cosmos itself. Quantum mechanics, with its strange and counterintuitive principles, does more than just revolutionize our understanding of the microscopic world. It challenges our very notions of reality itself. The philosophical implications of quantum mechanics run deep, touching on ideas about the nature of truth, observation, and the very fabric of existence. For much of the 20th century, the Copenhagen interpretation, developed by Niels Bohr and his colleagues, served as the dominant framework for understanding quantum phenomena. In this view, quantum systems are described by a wave function, which encapsulates all the possible states a system can occupy. However, when we observe the system, the wave function collapses, and the system assumes a single definite state. This concept of wave function collapse led to one of the most profound philosophical questions in quantum mechanics. What exactly happens during measurement, and what role does the observer play in this process? According to Bohr's Copenhagen interpretation, the act of measurement itself is a key player in determining the outcome of quantum events. Before measurement, particles like electrons exist in a superposition of all possible states. But once we observe the system, whether it's the position of an electron or the spin of a photon, the wave function collapses, and the system chooses a specific state. For Bohr and his followers, this collapse was essential to understanding quantum mechanics, and the observer played a crucial role in shaping the outcome. This view, though widely accepted for much of the 20th century, has been questioned over the years, as the implications of observer involvement seem to introduce a strange paradox. If the observer's role is so essential, does that mean that the universe only truly exists when we look at it? Does reality depend on observation? Enter the many worlds. Interpretation, MWI, proposed by Hugh Everett in 1957, which provides a very different answer to these questions. MWI suggests that rather than the wave function collapsing into a single state when we observe a system, all possible outcomes actually occur, each in its own parallel reality. According to MWI, when we measure a quantum system, the universe splits into multiple versions, each corresponding to one of the possible outcomes. In this view, there is no need for wave function collapse because every possible outcome of a quantum event is realized in a separate parallel universe. For example, in a quantum system with two possible outcomes, such as a particle being in two places at once, MWI suggests that both outcomes happen simultaneously, one in our universe and one in a parallel universe. This idea leads to the notion of an ever-branching multiverse, where every possible outcome of every quantum event is realized in its own separate timeline. MWI avoids the need for an observer-driven collapse of the wave function, offering a view of reality where all possibilities are realized in a vast multiverse of parallel worlds. The Copenhagen interpretation and the many worlds interpretation represent two radically different philosophical perspectives on the role of the observer in quantum mechanics. While Copenhagen suggests that observation is integral to the existence of a definite reality, MWI proposes that all realities coexist independently of observation, and observation merely reveals one of the many possible outcomes. Both interpretations challenge our understanding of objectivity and the nature of reality, but they do so in very different ways. David Bohm, another influential figure in quantum theory, also had his own views on the nature of quantum mechanics and its implications for reality. Unlike Bohr and Everett, Bohm proposed an alternative interpretation of quantum mechanics known as the de Broglie-Bohm theory, or the pilot wave theory. In Bohm's view, quantum systems are not governed by randomness or probability, but instead by deterministic trajectories that are guided by a quantum potential. This quantum potential provides the guiding force for particles, determining their paths in a way that is far more subtle and complex than classical physics would suggest. Bohm's theory challenges the traditional understanding of wave function collapse because, in his framework, the wave function never collapses. Instead, particles always have definite positions, but their behavior is influenced by the quantum potential, a hidden, underlying order that governs their motion. Bohm introduced the concept of the implicate order, suggesting that the apparent randomness of the quantum world is actually a reflection of a deeper hidden level of reality. This hidden order, according to Bohm, underlies all of space and time, and it is from this deeper level that the observable universe emerges. Bohm's ideas offer a perspective where time and space are not fixed, but are instead shaped by the flow of the quantum potential. His view of the universe is holistic, rather than viewing the universe as a collection of independent particles interacting with one another. Bohm saw it as a deeply interconnected whole, where everything is connected to everything else through the quantum potential. This holographic view of reality suggests that the universe is more like a vast interconnected web, where the properties of one part of the system influence every other part, even across vast distances. In many ways, Bohm's holographic view of the universe offers a way to resolve the contradictions that arise in quantum mechanics, especially when it comes to the role of the observer. In Bohm's framework, there is no need for the observer to collapse the wave function. Instead, reality unfolds from a deeper level of quantum potential, and observation is simply part of the process by which we interact with that deeper reality. This perspective opens up new avenues for thinking about the fundamental nature of space, time, and consciousness. Quantum mechanics, with its strange and often paradoxical nature, has forced us to rethink our most basic assumptions about the universe. As we explore the implications of quantum theory, we see that the very nature of reality is not as simple as we once thought. Is reality something that exists independently of us, or is it shaped by our observation? Do particles have definite properties, or are they merely potentialities until we measure them? These are questions that quantum mechanics poses, and they force us to reconsider the very idea of objectivity. As we continue to grapple with these questions, it's clear that quantum mechanics challenges our classical understanding of reality. Whether we subscribe to the Copenhagen interpretation, the many worlds interpretation, or Bohm's holographic view, one thing is certain. The universe is far stranger and more interconnected than we could have ever imagined. And as our understanding of quantum mechanics continues to evolve, it may provide new insights not just into the microscopic world of particles, but into the very nature of existence itself. The nature of time, space, and reality may be far more complex than we've ever realized, and quantum mechanics is giving us the tools to begin unlocking these mysteries. The world of quantum physics has not only reshaped our understanding of the universe at its most fundamental level, but it has also ushered in a new era of technological innovation. Over the past few decades, the strange and mysterious principles of quantum mechanics have found practical applications that are beginning to transform industries across the globe. These quantum technologies, once confined to the pages of scientific journals, are now finding their way into real-world use, promising to revolutionize everything from communications to medicine. One of the most exciting applications of quantum mechanics is quantum encryption. Classical encryption systems, such as those that secure online banking and communications, rely on the complexity of mathematical problems, like factoring large numbers, to keep information safe. While these systems are incredibly secure by today's standards, they are vulnerable to future technological advances, particularly the advent of quantum computers. Quantum computers, once fully developed, could easily break current encryption methods by using algorithms, like Shor's algorithm, that solve these problems exponentially faster than classical computers. To combat this, scientists have developed a new form of encryption based on the principles of quantum mechanics. Quantum key distribution, QKD, is a groundbreaking technology that allows two parties to share a secret key in a way that is absolutely secure. The key idea behind QKD is the no-cloning theorem of quantum mechanics, which states that it is impossible to create an identical copy of an unknown quantum state. This means that any attempt to eavesdrop on the key exchange would disturb the quantum state and reveal the presence of the eavesdropper. As a result, quantum encryption guarantees that any interception of the key will be immediately detected, making it much more secure than classical encryption methods. One of the most well-known examples of quantum encryption is the BB84 protocol, developed by Charles Bennett and Gilles Brassard in 1984. This protocol uses quantum bits, or qubits, to encode the key, and any measurement of the qubits by an outside observer would change their state, revealing the intrusion. In recent years, quantum encryption has moved from theory to practice, with companies like ID Quantique and Quantum Exchange offering commercial quantum encryption solutions. In fact, nations like China have already begun deploying quantum satellites for secure communications, marking a significant step toward building a quantum internet. In addition to encryption, quantum mechanics is making waves in the field of quantum sensing. Quantum sensors leverage the unique properties of quantum states, like superposition and entanglement, to achieve incredibly precise measurements of physical quantities such as time, magnetic fields, and acceleration. These sensors have the potential to surpass the performance of classical sensors by orders of magnitude, enabling new advancements in a wide variety of fields from medicine to navigation. One area where quantum sensors are already making a big impact is in magnetometry, the measurement of magnetic fields. Quantum sensors based on nitrogen vacancy centers in diamonds have been shown to measure magnetic fields with unparalleled sensitivity, allowing for high-resolution imaging of biological tissues and even the detection of single molecules. This has exciting implications for medical imaging and diagnostics, where quantum sensors could enable earlier detection of diseases like cancer or Alzheimer's by providing more detailed images of the body's internal structures. Another exciting application of quantum sensing is in gravitational wave detection. LIGO, the Laser Interferometer, gravitational wave observatory, has already made headlines by detecting ripples in spacetime caused by the collision of black holes. Quantum sensors, specifically quantum interferometers, could greatly improve the sensitivity of gravitational wave detectors, allowing scientists to observe even smaller and more distant events. This could open up a new era of astronomy, providing insights into some of the most extreme phenomena in the universe, such as the merging of neutron stars or the dynamics of supermassive black holes. As we venture into the world of quantum computing, the potential for innovation becomes even more exciting. Quantum computers are not just faster versions of classical computers. They represent a whole new way of thinking about computation. Instead of using classical bits, which can be either a 0 or a 1, quantum computers use qubits, which can exist in a superposition of both 0 and 1 simultaneously. This allows quantum computers to process massive amounts of information in parallel, solving problems that would take classical computers millions of years to solve in a fraction of the time. One of the most promising applications of quantum computing is in the field of artificial intelligence, AI. Quantum computers have the potential to drastically improve the efficiency of machine learning algorithms, enabling AI systems to learn from data much faster and more accurately than ever before. Quantum machine learning could lead to breakthroughs in areas like natural language processing, image recognition, and drug discovery. In fact, quantum computers could accelerate the development of AI by enabling more powerful simulations and optimizations, which are crucial for training complex models. Similarly, quantum computing has the potential to revolutionize drug discovery. One of the major challenges in developing new drugs is simulating the interactions between molecules. Classical computers struggle with this task because the number of possible interactions between molecules is astronomically large. Quantum computers, with their ability to simulate multiple possibilities simultaneously, could make this process much more efficient, potentially leading to faster discoveries of life-saving medications. Researchers are already using quantum computers to simulate the behavior of molecules at the quantum level, opening up new possibilities for designing drugs that are more effective and have fewer side effects. One of the most significant achievements in the quantum computing world came in 2019, when Google claimed to have achieved quantum supremacy. This milestone marked the first time that a quantum computer, in this case, their Sycamore processor, performed a task that would have been practically impossible for even the most powerful classical supercomputers. Google's Sycamore processor completed a complex computation in just 200 seconds, a task that would have taken a classical supercomputer more than 10,000 years to complete. While quantum supremacy is still a long way from practical large-scale applications, this achievement signaled the beginning of a new era in computing. Looking to the future, the possibilities for quantum technologies are limitless. Quantum communication networks, which will form the backbone of the quantum internet, promise to revolutionize how we exchange information. The quantum internet will not only offer secure communication channels through quantum encryption, but it will also allow for the sharing of quantum information between quantum computers, creating a global network of quantum processors that can solve problems beyond our current capabilities. This interconnected quantum infrastructure could lead to new breakthroughs in fields like artificial intelligence, medicine, and material science. Another exciting area of research is quantum teleportation. While it may sound like something straight out of science fiction, quantum teleportation has been experimentally demonstrated with photons and even atoms. Quantum teleportation doesn't mean transporting matter instantaneously across space, but rather transferring quantum information between distant particles without physically moving them. This could have profound implications for future communication systems, where quantum teleportation could be used to instantly transfer information across vast distances, making secure, ultra-fast communication a reality. In conclusion, quantum technologies are no longer just theoretical ideas. They're rapidly becoming a reality, with the potential to transform industries and solve problems that were previously considered insurmountable. From quantum encryption that ensures secure communication to quantum computing that could revolutionize AI and drug discovery, these technologies are poised to reshape our world. The road ahead is filled with exciting possibilities, and as we continue to unlock the potential of quantum mechanics, we're likely to see even more groundbreaking innovations in the years to come. Whether it's the quantum internet, quantum teleportation, or quantum sensors that can detect the most minute changes in the universe, the quantum revolution is only just beginning. Quantum mechanics, though often associated with the world of tiny particles and abstract equations, has profound implications for the way we understand the behavior of atoms, molecules, and even complex biological systems. At its core, quantum mechanics offers a deeper, more fundamental view of how matter behaves at the microscopic level, and this insight extends far beyond just the lab bench. It shapes everything from the bonding between atoms to the processes that sustain life. One of the most significant ways that quantum mechanics shapes the physical world is in the chemical bonding between atoms and molecules. In classical physics, we might think of chemical bonds as simple attractions between atoms, with electrons behaving like little particles that orbit a nucleus. However, when we bring quantum mechanics into the picture, we see that the situation is much more intricate. Quantum mechanics reveals that electrons do not orbit the nucleus in neat, predictable paths, as we once thought. Instead, they exist in probability clouds, where the electron's position is described by a wave function that shows the likelihood of finding the electron in a particular place. This wave-like behavior of electrons leads to the formation of chemical bonds, which are the result of complex interactions between atoms. When two atoms approach each other, their electrons overlap and form what we call molecular orbitals. These orbitals are solutions to the Schrödinger equation, which describes the wave function of the electrons in the system. Through this quantum interaction, atoms can bond to form molecules, and the resulting molecular structure dictates the properties of the substance. Quantum mechanics explains why atoms of certain elements form bonds in specific ways, why molecules adopt particular shapes, and why different types of bonds, such as covalent, ionic, and metallic bonds, exist. Without quantum mechanics, we wouldn't have a complete understanding of how the elements come together to form the vast array of molecules that make up the matter we encounter every day. Quantum mechanics also plays a crucial role in biological systems, where it shapes processes that seem far removed from the microscopic world of particles. Quantum biology is a relatively new field that explores the role quantum effects play in biological phenomena, and one of the most exciting examples is the process of photosynthesis. Photosynthesis is the way plants and certain bacteria convert light energy into chemical energy, and it is essential for life on Earth. For years, scientists understood the process primarily in classical terms, focusing on the chemical reactions that take place. But recent research has shown that quantum coherence, a quantum phenomenon where particles exist in multiple states at once, may play a critical role in how efficiently photosynthesis works. In certain plants, the energy from absorbed light is transferred through a series of molecules in what is known as the light harvesting complex. This energy is funneled into reaction centers, where it drives the chemical reactions that convert light into energy. What's astonishing is that experiments have shown that the energy appears to travel through these molecules in a way that can only be explained by quantum mechanics. The energy doesn't just follow a single path. Instead, it explores multiple pathways simultaneously in a phenomenon known as quantum superposition. This allows the system to find the most efficient path for energy transfer, even in complex environments where classical mechanics would predict a less efficient outcome. It's as though the molecules involved in photosynthesis are utilizing quantum effects to optimize their function, making photosynthesis one of the most efficient processes in nature. Another fascinating example of quantum biology can be found in avian navigation, the ability of certain birds to navigate long distances during migration. Researchers have discovered that birds may use the Earth's magnetic field to guide their way, and it appears that quantum mechanics is involved in this process. Specifically, birds are thought to rely on a quantum entanglement mechanism in their cryptochrome proteins, which are sensitive to light. The entangled quantum states in these proteins allow birds to sense subtle changes in the magnetic field, providing them with a kind of quantum compass that helps them navigate with astonishing accuracy over thousands of miles. Quantum coherence also plays a role in the broader field of biological sensing, where the ability to measure and respond to environmental changes is critical for survival. Many biological systems, from enzymes to proteins, exhibit quantum behaviors that enhance their efficiency and sensitivity, enabling organisms to respond to stimuli in ways that would be impossible under classical physics alone. Beyond the fascinating world of quantum biology, quantum mechanics is also revolutionizing fields like medicine, where the manipulation of matter at the quantum level is leading to new tools and techniques. One of the most exciting innovations is the development of quantum dots, tiny semiconductor particles that are only a few nanometers in size. These quantum dots have unique properties that arise from their quantum nature, and they are already being used in medical imaging and drug delivery systems. Quantum dots can be engineered to emit light at specific wavelengths, making them ideal for use in fluorescence imaging, where they help doctors visualize and track specific molecules within the body. Their tiny size and ability to be tailored to specific tasks make them incredibly useful in medicine, allowing for more precise and less invasive diagnostics. For example, quantum dots can be used to tag cancer cells, allowing doctors to identify and monitor the progression of the disease with much greater accuracy than traditional imaging methods. In addition to their use in imaging, quantum dots are being explored for targeted drug delivery. By attaching drugs to quantum dots, scientists can create delivery systems that release medication directly at the site of a disease, minimizing side effects and improving the effectiveness of treatments. This is especially promising for the treatment of diseases like cancer, where traditional chemotherapy often causes damage to healthy cells. With quantum dots, researchers hope to create more personalized and effective treatments that target only the diseased cells, leaving healthy tissue unharmed. The cross-disciplinary influence of quantum mechanics is far-reaching, impacting fields as diverse as chemistry, biology, and medicine. The ability to manipulate and understand matter at the quantum level has opened up entirely new areas of research, allowing scientists to create materials and devices with properties that were once thought impossible. For example, quantum mechanics has led to the development of superconductors, materials that can conduct electricity with zero resistance, and quantum batteries, which promise to revolutionize energy storage and efficiency. Quantum mechanics is also pushing the boundaries of nanotechnology, where scientists are exploring the potential of manipulating matter at the atomic and molecular levels. Quantum systems offer the possibility of building materials with incredibly precise properties, opening up new avenues for creating everything from faster electronics to stronger and lighter materials. The ability to control individual atoms and molecules could lead to breakthroughs in fields as varied as solar energy, space exploration, and computing. As we continue to explore the quantum world, we're likely to see more innovations that blur the line between science fiction and reality. From quantum encryption that promises secure communication networks to quantum sensors that could revolutionize everything from medical diagnostics to environmental monitoring, the applications of quantum mechanics are vast and diverse. The future of quantum technologies holds the promise of solving some of the world's most pressing challenges, from disease detection and treatment to building a more sustainable and secure world. With each breakthrough, we are getting closer to unlocking the full potential of quantum mechanics, and the possibilities seem almost endless. Quantum physics doesn't just help us understand the behavior of subatomic particles, it also holds profound implications for some of the biggest questions in cosmology, the study of the universe itself. The fascinating thing about quantum mechanics is that it doesn't just apply to the tiny scale of atoms and particles. It could, in fact, be the key to unlocking the deepest mysteries of the universe, how it began, what it's made of, and what the ultimate structure of reality is. At the heart of the connection between quantum physics and cosmology is the question of cosmic inflation. This theory, which emerged in the early 1980s, proposes that in the first moments after the Big Bang, the universe expanded exponentially, growing faster than the speed of a light. This sudden and rapid expansion could explain many of the large-scale features of the universe, like its uniformity and flatness. But what sparked this incredible expansion? According to the theory, quantum fluctuations, small, random changes in the energy of the vacuum, played a critical role. These fluctuations, which are predicted by quantum mechanics, could have caused tiny regions of space to rapidly inflate and grow into the vast, uniform universe we observe today. Imagine the early universe as a bubbling, energetic field, where quantum fluctuations were everywhere, occurring at the most microscopic level. These fluctuations weren't just random noise, they could have had real consequences, stretching tiny, minuscule areas of space-time into larger structures during the inflationary period. These primordial quantum fluctuations provided the seed for the large-scale structures we see in the universe today: galaxies, clusters of galaxies, and the intricate cosmic web that connects them all. In other words, quantum mechanics may have directly influenced the evolution of the universe itself, shaping the very structure of space-time in its earliest moments. But the role of quantum mechanics doesn't end with inflation. One of the most tantalizing possibilities that quantum physics presents is the idea that it may hold the key to understanding the origins of the universe. The current leading theory, the Big Bang, suggests that the universe began from an extremely hot, dense state, around 13.8 billion years ago. But what happened in the earliest moments, specifically the very first Planck time, which occurred within the first 10 to the minus 43 seconds after the Big Bang, is still a mystery. At these incredibly tiny timescales, quantum mechanics would have governed everything, and general relativity, the theory that describes gravity and the large-scale structure of space-time, breaks down. To fully understand the universe's beginnings, we need a theory that can reconcile both quantum mechanics and general relativity. Currently, we don't have a complete understanding of how these two theories can coexist in the early universe, but the search for a unified theory, often called a theory of everything, TOE, is one of the greatest quests in modern physics. A unified theory would describe all the fundamental forces of nature: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, as manifestations of a single all-encompassing framework. In many ways, this search is the holy grail of theoretical physics. Quantum mechanics provides the language for describing the small-scale forces, while general relativity governs the large-scale structure of the universe. But these two theories are fundamentally different in the way they describe space, time, and forces. Quantum mechanics views particles and fields as discrete and probabilistic, while general relativity treats space-time as a smooth, continuous fabric. The challenge, then, is to unify these two frameworks into a single theory that can describe both the quantum and the cosmic. One approach is string theory, which suggests that the fundamental constituents of the universe are not point-like particles, but rather one-dimensional objects known as strings. These strings vibrate at different frequencies, giving rise to different particles and forces. String theory also predicts the existence of extra-spatial dimensions, dimensions beyond the familiar three of space and one of time. While string theory holds promise as a candidate for a TOE, it is still in the realm of theoretical research, and much more work is needed to test its predictions and understand its implications. Another approach to unifying quantum mechanics and gravity is loop quantum gravity, a theory developed to describe the quantum properties of spacetime itself. Unlike string theory, which relies on the idea of extra dimensions, loop quantum gravity suggests that spacetime is made up of tiny discrete units, much like the pixels in a digital image. These units form a network, or loop, and the smooth geometry of spacetime we observe at macroscopic scales arises from the interactions of these loops at the quantum level. This theory could potentially explain the behavior of gravity at the smallest scales, where quantum mechanics and general relativity collide. While we don't yet have a final theory that can fully reconcile quantum mechanics and gravity, the ongoing research into quantum cosmology is shedding light on the deepest questions about the origins of the universe. One of the key challenges is understanding the nature of singularities, such as those that lie at the centers of black holes or at the very beginning of the universe. At these points, the equations of general relativity predict that the curvature of spacetime becomes infinite, and the laws of physics break down. Quantum mechanics, with its probabilistic nature, offers the possibility of avoiding these infinities, potentially providing a more complete understanding of these extreme environments. Another avenue for exploring the early universe and the connection between quantum mechanics and cosmology lies in the study of quantum fluctuations in the cosmic microwave background, CMB. The CMB is the faint glow left over from the Big Bang, and it provides a snapshot of the universe when it was just 300,000 years old. The tiny variations in temperature observed in the CMB are thought to be the imprint of quantum fluctuations that occurred during the inflationary period. By studying these fluctuations, scientists hope to gain insights into the quantum processes that occurred at the very beginning of the universe. The search for a unified theory of everything also has profound philosophical implications. If we are able to understand the quantum nature of the universe, we may gain a deeper understanding of reality itself. Quantum mechanics challenges our most basic assumptions about the nature of space, time, and causality. It shows us that the universe is not as deterministic as we once thought. Rather, it is a world of probabilities, where the future is not set in stone but exists as a range of possible outcomes. This insight could profoundly reshape our understanding of objectivity, causality, and the structure of reality itself. As we continue to explore the mysteries of the universe with the tools of quantum mechanics, we are likely to uncover new insights that not only explain the origins of the universe, but also provide answers to some of the deepest questions about existence. From quantum fluctuations in the early universe to the search for a theory of everything, quantum mechanics offers a path to understanding the very fabric of reality itself. And while we're still far from having all the answers, Each new discovery brings us closer to understanding the most fundamental aspects of the cosmos: how it began, how it works, and perhaps even how it will ultimately evolve. The future of quantum physics is brimming with possibilities, offering the potential to unlock some of the most profound mysteries of the universe. As we stand on the precipice of new discoveries, quantum mechanics continues to challenge our understanding of the very fabric of reality. One of the most exciting frontiers in quantum physics is the search for quantum gravity, a theory that would unify the two pillars of modern physics: quantum mechanics and general relativity. These two theories have been incredibly successful in their respective domains. Quantum mechanics governs the smallest particles in the universe, while general relativity describes the force of gravity and the large-scale structure of the cosmos. However, they are fundamentally incompatible when it comes to the extreme conditions found near black holes or in the very early universe. Quantum gravity aims to provide a framework that can describe both the microscopic and cosmic scales in a single, coherent theory. The search for a theory of everything, TOE, which would explain all the fundamental forces of nature in one elegant theory, is another crucial area of exploration. The TOE would reconcile the quantum world, governed by probabilities and uncertainties, with the smooth, deterministic fabric of space-time described by general relativity. A complete theory of quantum gravity could also shed light on the elusive nature of dark matter and dark energy, which make up the vast majority of the universe's mass and energy, but remain largely invisible to current scientific instruments. As researchers continue to probe the depths of quantum physics, there are several key challenges that stand in the way of future breakthroughs. One of the biggest hurdles is maintaining quantum coherence in large systems. In the quantum world, particles can exist in multiple states at once, a phenomenon known as superposition. However, when these quantum systems interact with their environment, whether it's a bit of stray light or heat, this coherence tends to collapse, and the system behaves more classically. This phenomenon is known as decoherence. Achieving and maintaining quantum coherence in large complex systems is crucial for the development of quantum computers, sensors, and other technologies. The challenge lies in scaling up quantum systems without losing the delicate quantum properties that make them so powerful. This brings us to one of the most exciting applications of quantum physics: quantum computing. Quantum computers have the potential to solve problems that are currently intractable for classical computers, from simulating complex molecular structures to optimizing large-scale systems. However, there are still many technical challenges to overcome before quantum computers become widely available. One of the main obstacles is scalability, building a quantum computer with enough qubits to perform meaningful computations while maintaining coherence over time. Companies like IBM, Google, and Microsoft are all working toward this goal, but the road ahead is long. Even so, the progress made so far has been staggering. In 2019, Google claimed to have achieved quantum supremacy, demonstrating that a quantum computer could solve a problem faster than the most powerful classical supercomputers. While the problem they solved was specific and not directly applicable to most real-world applications, it marked a significant milestone in the race to build practical quantum computers. Looking ahead, the future of quantum computing holds incredible promise. As quantum computers become more powerful and reliable, they are likely to have a transformative impact on a wide range of industries. One area where quantum computing could make a huge difference is in artificial intelligence, AI. Quantum computers have the potential to speed up machine learning algorithms by processing vast amounts of data in parallel, enabling AI systems to learn faster and make more accurate predictions. Quantum machine learning could lead to breakthroughs in everything from personalized medicine to climate modeling. With the ability to handle much larger datasets and solve more complex optimization problems, quantum computers could take AI to a level that's currently unimaginable. Another field that quantum mechanics is poised to revolutionize is drug discovery. Classical computers struggle to simulate the behavior of complex molecules because the number of interactions between atoms grows exponentially as the size of the molecule increases. Quantum computers, however, can process this information in parallel, allowing researchers to simulate the interactions between molecules much more efficiently. This could lead to faster and more accurate drug discovery, ultimately accelerating the development of new treatments for diseases like cancer, Alzheimer's, and more. By simulating the behavior of molecules at the quantum level, quantum computers could help researchers design drugs that are more effective and have fewer side effects. As quantum technology advances, its impact on energy production and environmental sustainability could also be profound. Quantum systems could be used to improve solar panels and energy storage systems. For instance, quantum sensors could allow for more efficient monitoring and control of energy systems, improving their efficiency and reducing waste. Additionally, quantum technologies like quantum dots, tiny particles that can absorb and emit light, could be used to enhance the performance of solar cells, making them more efficient at converting sunlight into energy. In the future, quantum batteries, which store and release energy in ways that classical batteries cannot, could lead to significant improvements in energy storage and distribution. Beyond specific industries, quantum advancements will likely have a broader impact on society as a whole. Quantum communication systems, which rely on the principles of quantum entanglement, could provide a level of security that's currently unimaginable. Because quantum communication is based on the no-cloning theorem, which prevents anyone from copying quantum information without detection, it offers the promise of unhackable communication networks. This could transform everything from banking and military communications to everyday internet usage. The potential for creating a quantum internet, a network based on quantum principles of security and information transfer, could fundamentally change the way we connect with each other, making online communication more private, efficient, and secure. The societal impact of quantum breakthroughs will not be confined to technology alone. Artificial intelligence, medicine, energy, and communications are just the beginning. As quantum technologies continue to advance, they may even lead to a deeper understanding of the fundamental nature of reality itself. Just as classical mechanics once helped us understand the behavior of the visible world, quantum mechanics could offer insights into the fabric of space-time, the origin of the universe, and perhaps even the nature of consciousness. With each new discovery, quantum physics is taking us closer to understanding the deepest mysteries of existence. In the coming decades, as quantum mechanics continues to make its mark on science and technology, it has the potential to revolutionize industries, solve critical problems, and shape the future in ways we can only begin to imagine. While there are certainly challenges ahead, the promise of quantum physics is undeniable. Whether it's powering the next generation of computers, enhancing our ability to communicate securely, or enabling breakthroughs in medicine and energy, quantum mechanics is not just a subject for physicists, it's the key to unlocking the next frontier of human innovation. Throughout this exploration of quantum physics, we've journeyed through some of the most profound and fascinating aspects of the universe. We began by understanding the core principles of quantum mechanics, ideas like superposition, where particles exist in multiple states at once, and entanglement, where particles are mysteriously connected across vast distances. These principles defy our everyday experience of the world, but they also unlock new possibilities that have reshaped not only science, but also the technology we use daily. We've seen how quantum mechanics has influenced the development of quantum computers, capable of solving problems that classical computers could never approach in a reasonable time. Quantum technologies are already making a huge impact in fields like cryptography, ensuring secure communications, and in medicine, offering new tools for diagnostics and treatment. We've explored how quantum mechanics is not just a theoretical framework, but a powerful engine driving advancements in modern science, from chemistry and biology to cosmology, and the understanding of the universe's origins. One of the most exciting aspects of quantum mechanics is its ability to reveal deeper mysteries of reality. The question of how time flows, why the universe behaves the way it does, and how everything from the fundamental forces of nature to the very structure of space-time came into being, all of these puzzles may ultimately be answered by the quantum world. Quantum mechanics doesn't just give us tools for making better devices or more efficient systems, it offers insights into the very nature of existence itself. As we continue to unlock the secrets of the quantum world, it's clear that we are only scratching the surface. From the ongoing search for quantum gravity to the quest for a theory of everything, there is still much to explore. Each discovery opens up a new realm of possibilities, and with it, new challenges. The quantum revolution is still in its early stages, and the potential to transform science, technology, and even our understanding of life itself is limitless. So whether you're a scientist, an engineer, or simply a curious mind, the world of quantum physics invites you to keep exploring. The possibilities are infinite, and with every breakthrough we move closer to unveiling the mysteries of the universe. The quantum revolution is unfolding before our eyes, and it will continue to shape the future in ways we can only begin to imagine. The journey is just beginning, and who knows what incredible discoveries lie ahead.